Good afternoon, everyone. It's pretty late, I understand. But my name is Sylvain Chenard. I'm a quantum safe network solution leader at Nokia. And we're going to, spend some time with you to go in some of the detail of, how to deploy, those type of solution that we just saw. And also like different aspect of what does it mean to be quantum safe, the outcome. Peja?
Yeah, and I'm Peja Dragovic. I'm leading the PLM in product evolution and security. And as Sylvain pointed out, and the good news though, right, even though we're toward the end of the day, a lot of stuff has already been mentioned. So we're going to be able to curtail a little bit our speech and mostly agree with our predecessors. So let's just kind of get started, and hopefully we won't stop you from having early dinner.
Yeah, I just want to start. And one thing first that I want to say, this is really comforting. Over the 2 days, we saw a lot of the good message, right? I mean, everybody kind of agree on the outcome. We need to become quantum safe. There's definitely multiple techniques how to become quantum safe. And like from using a combination of mathematics and physical entropies, whether they are quantum from quantum physics or classical physics, we need to protect different type of level of network. And this is a bit something we're going to talk during this presentation, whereas a lot of people thinks about the actual application. Like everybody knows in our phone when you communicate, we have established an end-to-end communication, first level. And it's usually very much dynamic. And the dynamicity is very applicable for PQC algorithms, right? You tear up a session, close down the session, and move on, right? But as you go down into the network, because viewed from a network-centric type of designers, there's a huge amount of stuff going down the pipe. And it's usually more applicable for classic physics to provide an entropy that will stay a long time. The keys exchange and all those techniques could be different, but all of them has a role to play. And and today we're going to talk right now in this session more on a layer that we didn't talk much today, the OTN layer.
Step in here. So as we said earlier, right, defense in depth is something that we probably agree that this is a good idea. It's going to give us like, security at every level, and layer one, for example, being the first line of defense, followed by multiple, other layers, right? Now, I'm going to focus on layer one and try to kind of provide a bit of an overview of what are the specific value propositions that layer one encryption at layer one does, in addition to just having it like defense in depth. So this slide I'm going to quickly just glance through, given that Farzam and a few others already mentioned. The whole point that I wanted to make with this slide is that optical networks, real optical networks today, are fairly different from what we are seeing initial set of QKD type of implementations, being able to demonstrate or prototype, right? So we need to be cognizant of that, right? And find proper methods to actually deal with it. So at the end of the day, symmetric ciphers are the way to, provide quantum safe solution. Symmetric key distribution down to individual nodes, again, the same. And we need to deal with distances, with the different impairments, the topologies, and with Farzam kind of very nicely kind of presented. It's not just the distance and insertion loss. There are various other nonlinear effects that we encounter in those types of networks, whether regional, long distance, or subsea, right? So the one little thing that I wanted to add here is, well, we are kind of dealing with these distances, complexities in, larger network contexts. We also have optical networks in the edge, right, which don't necessarily have a problem of distances and optical impairments, etc., but do have a problem of potential kind of nodes of trust or ability to kind of in a commercially viable way provide those symmetric keys down to the edges of the network where certain encryptors need to be placed. Now, We did speak about, encryption most of the day, right? And how to prevent from using the data in nefarious fashion, but preventing data from being harvested in the first place, which was also kind of addressed by my predecessor, Eyal, right? Optical layer, photonic layer, conventional network-based photonic layer does provide ability to actually monitor the network and detect potential nefarious activity, right? So one of the areas where there's a lot of research and development being done lately is ability to do network sensing utilizing data that is already available within the digital signal processor that we have today, right? We're typically using state of polarization vector and its kind of samples to characterize certain physical or electromagnetic type of events along the path of the photon beams detected at a receiver, and that way, we have ability to actually, provide signature of certain events. For example, if there is a fiber bent or some tap that somebody would have tried to, drop the signal and be able to harvest, would be relatively, consistently, detected and registered by ability to monitor state of polarization vector. So just to give you an idea how sensitive and how capable this method is, that we've run some experiments over the Atlantic, subsea cable that was buried about a meter underneath the surface. And by monitoring state of polarization vector, we were able to actually assess the wave swells 1,000 meters or so on the surface of the water by just looking at polarization data, right? The other method is relatively straightforward, the optical time domain reflectometer that provides also characterization of the fiber and ability to detect certain deviations for baseline state where we can potentially determine whether there is some nefarious activity that we would want to prevent. Now, the rest of the slides, I'm going to focus on a couple of things that are very characteristic in layer 1 encryption, right? So we're talking about photonic layer. So optical transport network have like layer 0, which is photonic layer as we typically kind of call it, and then electrical domain, which is the OTN layer, right? So the encryption, outside of what we've just heard earlier, right? Today is quite readily available at layer 1, right? And there are some characteristics besides just having it quantum safe that can actually, and defense in depth being multiple layers of encryption, there are some characteristics of layer 1 that would be beneficial and demand actual layer 1 encryption to have in our networks. So one of the things that layer 1 networks generally have is transparency, right? So the good thing about transparency is, you can have multiple different signal types or bit streams transported without losing any characteristic information, and, not just pure bit stream, but also timing, etc., right? Now, one thing that is also, good about layer 1 encryption is that we're encrypting the bit stream, right? So in other words, we're obfuscating the data, and we are, preventing potential intruder from selectively kind of harvesting different packets, right? So we can't really focus on specific bit streams or packet streams or protocols that we would then, harvest in order to be able to decrypt later. In this context, even if there's no data, there's no packet flowing through a particular link, potential intruder would have to actually harvest the whole bit stream, and that puts a significant strain on their resources in order to be able to potentially use that in the future as decrypting. Latency at layer 1, the overall implementation dependent, but we can achieve latencies of several hundred nanoseconds to a few microseconds. So in that context, latency is not a factor, right? It's comparable to several tens or hundreds of meters of fiber propagation delay. Efficiency, right? So layer 1 is generally efficient, right? So transport power per bit, at physical layer or layer 1 is generally, fairly efficient comparing to other transport domains. However, the efficiency also can be measured in how much overhead we use to do encryption and how much the actual data is being transported. And in that context, layer 1 does provide a pretty efficient way of doing the encryption, besides the fact that it uses already established overhead rather than adding the overhead in order to accomplish encryption, right? And then last but not the least, if you look at the power needed to, or power contribution of encryption in a particular DSP or framer, we're, for example, seeing something like 1.2, 1.3% of added power, right, to the device, whether DSP or a framer, in order to actually enable encryption. So from that point of view, it's quite efficient way of, implementing the encryption, right? Reach, there's no limit in reach. Well, I would take that back. There are limits, but actually we can demonstrate, and we've heard earlier as well that thousands of kilometers of repeated, right? Not optically, but electrically unrepeated, right? The signals, right? Reliability. So using the conventional networks, we can provide various different protection methods and ability to do redundancy in terms of end-to-end services with encryption enabled. And then last but not the least, it scales from 1 gig to 800 gig today with available devices. And, it linearly scales, and there's no resource or power or other constraints that would prevent us from scaling to next generation type of client signals. Now, when we start kind of doing layer 1 encryption, in our networks, right, we need to kind of, define certain use cases, and where it's unreasonable to expect customers to go and rebuild networks or do forklift upgrade to certain network configurations. So the two typical use cases that we see people or customers deploy layer 1 encryption are, there's what I call brownfield type of implementation, where OTN layer encryptor can be placed in a particular, secure perimeter facility, and then utilize existing third-party or non-encrypt network, OTN network, to provide end-to-end encrypted services or connection. The only thing that would be needed in this case is transparency for certain overhead fields that would be needed to establish end-to-end, encryption between those two endpoints. And then the other use case would be like fully encrypted OTN network, where every link, is, encrypted, and we provide infrastructure encrypted at layer 1, such that any service that is transported through that network is encrypted. There would be some, use cases that are kind of in between these two, but these two are kind of the most representative of what we see customers go with. And then last but not the least, I want to kind of comment a little bit about the state of the art and where we are in terms of encryption capability. So I guess my colleagues would also testify that pretty much all devices with their framers, where the DSPs, various types of FPGAs or codes that exist out there, are capable of doing fairly efficient implementation at symmetric ciphers like AES-256. From the resource point of view, from the memory allocation on those devices, there is no constraint or a concern of implementing layer 1 encryption in various different points in the implementation of the device. We are seeing even like different framers that have a number of different points where ciphers are implemented, so we can do different configurations through the device, right? So from that point of view, devices out there available today are ready to be quantum safe, right? Then it comes down to implementation of quantum safe, end-to-end encryption, which, in our view, relies on symmetric key distribution and avoiding having any type of asymmetric or vulnerable kind of key agreement exchange across the data path. So in that context, we are, implementing from Nokia side, and we are promoting and deploying centralized key generation with quantum safe key distribution to endpoints, where we would then employ devices with the symmetric cipher and provide end-to-end quantum safe solution with in a scalable way. And then Sylvain, I'll kick it off back to you, so you can talk a little bit about the key generation and distribution based on our implementation.
Yeah, as Peja said, it's all about the key, right? I mean, everybody has locks, AES-256. But what makes the difference? Your message being protected from another one is the key, right? Well, simple is beautiful. Further down this slide, what you see is like the normal manual key exchange. Whereas you take the key, people, like, it's a manual process, it's written down, and they go change the keys all the time. It doesn't scale, but it's extremely secure. It's the case in very, very mission critical networks. Then there's ways to automate the key exchange. And we call here pre-shared keys. So the automations here, it's actually taking a real key using classical physics. We're not here yet with quantum key distribution or quantum key generation, but it could also be quantum number generator. And then the key is actually exchanged. It is transported to the endpoints. And these links, where the key is transported, it's actually quantum safe, has to be quantum safe. And in some of our reference blueprints, we're using the far left, right? The manual key, pre-shared keys setup. And therefore, we can automate the key very fast, the session keys, like the SAC, and you can exchange it as fast as you want. But we just move the simplicity here, like the KEK, like the key encryption keys used to encrypt the SAC, don't need to rotate as fast as the other ones. I mean, the traffic is lower, and it can be totally acceptable here. You see at the bottom, right? I mean, we have key exchange at the router level at MACsec. So the keys are produced at the layer, and we're using a KEK from the centralized key generator using classic keys to encrypt the KEK around it. Now, you could probably see like a themes here in between. Again, it is a simple concept. Whereas the centralized key authority that automate the distribution becomes an orchestrator. That's really complex. The orchestration, when you read in literatures or discussion in forums, the tendency of mixing the network management system and the security operations center, which usually you decouple, right? So this type of concept here, you have one element in the system, of course, high available, which actually has the topology of the network. So you don't have to push the topology of the network into the quantum key management system. Make it much more simpler in configuration. You keep it at the lower level where you do the network topology setup. And then instead of producing a key in the centralized environment, this orchestrator requests a key to the quantum key generation plane, and the keys is pushed down to the NE. Why this is actually good is that because we can do it in hybrid mode. This element can still produce a classic key. And one thing that is really important, it's always the crypto period. So, I mean, nothing's bad here. I mean, there's some limitation into the quantum key distribution mechanism, whereas sometimes there might be mechanical perturbations, there may be multiple things that may prevent the key to be recreated on the other side. And it's going to get better over time. But for now, if you want to do it now, you need to make sure that the crypto period is respected. So this element will detect if a key has been produced or not in the quantum domain. If not, it will make sure that the key is pushed down. Still a very safe key. It's a quantum safe key, which is generated by a classic physics generator. And of course, this is the same kind of things we talked a few minutes ago regarding the satellite. The satellite, there's no, between the third one versus the fourth one, there's no modifications in how you perform the management orchestration of the key. It's just using a different mechanism, a satellite in this case, to transport the key, while in fact transport and teleport the key, depending at which point in the equation you're doing it. So very simple, same solution. Doesn't mean that the one over there is less secure than this one. It's the same solution, different implementation, and they can coexist. You can have multiple layers or connections that can use the second one or even the first one. Whereas you implement for another section of your network, you can have terrestrial QKD or satellite QKD. It's the same implementation. Okay, thank you. This is a use case here. I'm going to go fast because I apparently have only 3 minutes left. So usually this is how we see it, right? An implementation where we have QKD, like either transport or satellite, and it's actually providing keys to the optical layer. A SAC using QRNG or even TRNG, and pair with AES-256. There's a SOC. This is important at the top, right? There's a SOC and the NOC. They're separate. In implementation, deployed in network, this is really, really different. So now it will look a little bit more complex, but it's simple. And it pair two types of paradigm that I just showed you the slide before. So the QKD environment still provide keys to the optical level, the layer 1. But also, you can see that the SOC at the top can provide keys to the optical layer in case the QKD domain does not produce a key, guaranteeing the crypto period. And here we have also a MACsec type of representation here, whereas the key, the KEK, the key that is used to encrypt the key to be sending between the two nodes, the SAC that is produced locally, is actually produced by the centralized management system who's pushing the key down and actually make sure that everything is quantum safe. Now, an important link, what we call the dynamic duo. The NOC is providing information of the topology that needs to be secure. It doesn't mean this is the entire network management system topology view. It just provides, here's what you need to secure in this network, push it down to the SOC. We talked a little bit about last mile. We can do a lot of things for the last mile, but we also, you see here, this is also a proposal, whereas you don't necessarily need to use necessarily everywhere, as I said, a combination of QKD domain, and here it's a purely classic physics keys for the last mile. And the last mile could be an optical last mile, a CPE, or it could be like a MACsec, or even any sec, or in the future, any other things you would like to. So this is really simple. There's a lot of lines, but when you get the slide, read it. It's really, really easy. It's really simple. So now, do you want to start with that?
Just a quick takeaway, basically. I just basically want to state, given that layer 1 encryption gets significant benefits, it's really low cost in terms of implementation, in terms of other kind of efficiency factors. It's really low, cost or available today, right? The customer, could ask a question: can we afford not to have layer 1 encryption in this defense, in-depth type of approach? And my answer would be not really. I mean, enabling layer 1 encryption makes a lot of sense. It provides a lot of benefits. It's available and quantum safe now, and that's the way to really recommend to our customers in the network.
Let me add a little few things in adapt and scale and evolve. Adapt, we talked a lot about new interfaces. ETC014, ETC04, to talk to the actual encryptors. Let's call it like MACsec, AnySec, or layer 1 encryptions. Well, don't forget about brownfield deployment. If you want operators to adopt this type of technology, you need to be able to adapt to the network that already exists. So very few, just the new devices, new latest release have those interfaces, but there's a lot of opportunity out there to upgrade the network. So we need to think about that, adapting this way. There are multiple blueprints implementation that I showed, right? It also means not every level in the network needs the same key distribution. So adapting based on the use case and the outcome. Scalability, it's always number one, right? You need to be able to provide something that is scalable, but it doesn't mean you have to encrypt the entire network, okay? And it doesn't mean you have to encrypt the network or secure the network the same way, depending the zone or the domain of traffic. Evolving, Peja mentioned layer one encryption, okay? And one of the aspect of it, it provides a cladding mechanism. So we need to give to upper layers the crypto agility. We all know, I heard multiple times today, right? PQC is there, it's gonna come. But me personally, I see that as that we're just pushing the time where it's gonna be cracked. So, RSA, DFL-man, for sure we have proof it's gonna happen. Lattice-based algorithm, we won't have time. We won't have 40 years to do it. It's gonna come too. So having the cladding at layer one helps you to change the algorithm at the top, still protecting your environment. On that note, thank you very much. I hope you all have a great evening.